Hey everybody, welcome back to Intermediate Motor Controls. We are what I like to consider at the pinnacle of our motor control journey. I like to wind up this whole motor control series with variable frequency drives. Okay, it's the newest technology for three-phase motors and how to control them. We've controlled them, we've started them, stopped them, reversed them. We've done all of that with basically older technology through motor starters, across the line starters. Okay, and we've done some braking with those too. But this is a newer technology that's been here since around the mid-1980s. Okay, so that's kind of why I like to do this at the end. It brings the latest technology, but you still have to have a strong understanding of what we've covered so far. That's why I don't like to teach it first, because it's going to be too many variables moving into variable frequency drives, and so it's a little bit more confusing. So this is why I say what I consider the best of the last. It's the most fun for me too. I think you'll enjoy it as well. So we're going to move right into drives today. Okay, as with the other technologies and the other components that are manufactured, there are a ton of manufacturers out there. I personally like Allen Bradley. I cut my teeth on them, and then I just like the PLCs. I like the drives. They're so easy to configure. But there are a ton of other manufacturers. There's ABB, Mitsubishi, Square D, Cutler Hammers now making drives and things like that. So there are a ton of manufacturers, but they all work the same. That's the nice thing about them. A drive is a drive is a drive, okay? And you're going to see that in just a minute. I'm going to explain. The biggest thing is going to be the number one is the horsepower difference that they can run a motor, and also just kind of how you program your parameters, establish your parameter listings and stuff like that. But we'll get into all that. So let's go ahead and move forward. First of all, back in the day, it used to be the only way you could control a speed of a motor. The speed of a motor is through a DC motor, okay? Well, if you remember in 1401, you took your three-phase induction motor apart, and you basically had a rotor, solid rotor, with the, well, wasn't solid, it was laminated discs in that rotor, okay? And then you had your stator windings, and you had your end bells that had a couple of bearings in it. That's pretty much it. Took them apart, put them together really fast, you tested the windings, it didn't take very long. A DC motor, however, is a lot more complex. You've got rotor windings, okay? You have the rotors actually wound. And you have the stator that's also wound as well. You have a commutator that has carbon brushes on there, carbon brushed springs. All of those things are more components to fail, okay? So, like I said, back in the day, the only way to control speed of a motor was if it was a DC, okay? It had a physical, a bigger footprint than its AC counterpart. In other words, a 10 horsepower DC motor was a lot bigger than a 10 horsepower AC motor, all right? So the physical size and also the weight and everything, those things were really heavy. And again, like I said, there was more components to wear out on you and to fail, okay? And there was more maintenance to do. Carbon brushes are constantly having to be changed due to wear, because they wear down to basically nothing, and then the motor quits. You have to go in there and do maintenance on it. So it's just more things to fail. And also the drive part of it that makes the motor run was more complex too. But in the mid-1980s, they came across a new technology. It's called variable frequency drives. Yeah, and by the way, that's not me. And that's not me either. But anyway, back in the 80s, these drives came on board. It gave us the option of controlled acceleration, controlled deceleration. Okay, we could, how fast we sped a motor up and brought it back down to zero, we had control over that. Okay, we had various braking methods. We talked about braking a couple weeks ago, and so with different ways we could make that motor stop, even with a drive. Okay, very, very efficient when it comes to running motors on drives. As an example, you could be running say a 10 horsepower motor at 100%, okay, 60 hertz. And if you say you're running a fan or a pump, if you bump the frequency down to 50 hertz just by 10 hertz, the savings of the electrical savings are about 50%. So just taking it down 10 hertz saves you about 50%. Now it's not linear, it's exponential, so the savings are not as great as you continue to ramp down. But I mean, that's just an example of how they're so efficient. Okay. Drives also provide us with diagnostics on board. It can give us some hints as to whether it's in the drive or if we've got a problem with the motor. I've had to go out before with some plants and they've had trouble with a drive and a motor. They didn't know which one it was. Real easy to tell. Okay, we're going to talk about that as well. But it also can be controlled by a PLC. A lot of drives have the push buttons on the front, the little operator keypad that you can start, stop them, and ramp them up and down. But it can also be controlled through a PLC, and they're now to where you can control them over Ethernet. So you don't necessarily have to have the hard wiring. Okay, so you can control them over a network. Okay. And a couple of other things that it does for us as well, it eliminates some components. Here we have the drive in the three-phase path going to the motor. But we can do away with motor starters, seal-in circuits, the contacts, okay? Remember we said contacts and starters were sources of wear and failure. You don't need a control transformer either. So, you know, again, you're going to have some input devices, possibly, not always, but there's options for that. But it does eliminate a lot of other components too. So, how does this work? How does this make the speed change? Okay, we got to back up to our 1401 lessons on how we come across this, or how we come about a certain speed on a motor. Okay, so here we have a 4-pole motor, and remember, a 4-pole motor is the number of poles per phase. Okay, you're looking here, this is like there's 12 poles. No, it's not a 12-pole motor. This is a 4-pole. You have 1, 2, 3, and 4. If you can see it well enough, these are A1s and A2s. Those are the A coils. The blues are the Bs, and the brownish ones are the C coils, or the C-phase coils. Okay, so we have 4 coils for the A phase, or for each phase. So this is going to be a 4-pole motor. All right. So our formula for determining what the speed of a motor is going to be, the synchronous speed. We're not going to talk about slip right now, but the synchronous speed is going to be 120. Which is a fixed number, times the frequency. Now the frequency is the power supplied by our power company. And here in the United States, North America, it's 60 hertz, okay? So it's 60 hertz, so 120 times 60 divided by the number of poles in the motor, which this is a 4-pole motor, all right? And that gives us a speed of 1,800 RPMs, all right? Now, there's a couple of things we can do. Like I said, this is a fixed number, and we can't really change the poles in the motor. We can, but it's not a very efficient way of changing the speed of a motor. Plus, it's still a fixed speed. So changing the poles in the motor, that's not a good option. So we're going to be stuck with the number of poles, and 120 is our fixed number. So what we're going to do is we're going to change the frequency at which we apply voltage, the power signal to the motor. Okay, so let's work that out a little bit. Again, 120 is our fixed number. Still a 4-pole motor. Now we're going to run it at 30 hertz. Okay, now we can't change the power from the power plant, but with a drive, we can change it to whatever we want to. Okay, so let's say we just theoretically change it to 30 hertz. Our 120 times 30 divided by 4 gives us a rotor speed of 900 RPM. So what we've done is we've cut that motor shaft speed from 1,800 to 900, cut it in half when we cut our frequency in half. Okay, it's going to be real critical. You'll start to see this in just a second. But again, drives all work the same way. They've got the 3 basic components. All of them have 3 basic sections. And again, some of the features as far as the parameters and things like that, the horsepower that it can handle, things like that. That's what separates the drives. But they're all the same. Okay, we're going to go over the 3 sections of the drive. Okay. First of all, we have the converter section, okay, or the input section, that's sometimes called. I'm going to break each one of these down for you. This is called the DC link, or sometimes called the DC bus, all right? And it's where we have DC power. And then we have the inverter or power section that actually hooks to the 3-phase motor. Now you'll notice over here that in the input section, or the converter section, we're putting 3 phases of power. Let me stop for just a second and show you this drive here. We should have probably maybe done this earlier, but that's okay. This is a little Allen Bradley 160 variable frequency drive. This is the one you're going to be working with in the lab. And you're going to you're going to hook your 3-phase up here, okay? And then you're going to have the 3 power leads that come out of the bottom of it. And that's really just about, you could get by with just those 6 conductors. The 3-phase going in, and the 3 phases out to the power, and you can control everything like that, and you're done. Okay, just that simple. okay? But here's your L1, 2, and 3 right there, and this is where you'll hook the L1, 2, and 3 right here. It's labeled as, sometimes it's labeled as R, S, and T. It's also listed as L1, 2, and 3 right here, these three terminal strips right there, or terminal points. So what we're doing here, the first thing we're doing, we're going to take the 480 volt, we're just going to use 480, okay, as it could be 208, okay, but we're going to use 480 volts, and we've got 3 phases of power, 120 degrees apart. I've kind of offset the 3-phase sine waves here, and they're 120 degrees separated from each other, okay, and so if you remember these from braking, okay, these are diodes, and they allow the positive half of our sine wave to pass while blocking the negative, and then in turn, this one is going to allow the negative to pass while blocking the positive, all right? And each phase has its own set of diodes to block and to allow to pass the voltage, depending on if it's positive or negative. And what that winds up giving us is DC voltage, okay? Remember, with the rectifier for our braking module, we took the sine wave, the AC voltage, and we used a bridge rectifier to give us DC voltage to inject into the windings. Well, the same thing's going on here with this. We're going to allow the positive voltage to come up to here and the negative voltage right here, and that gives us our next section, which is the DC bus. All right, so we've now got AC over here, but after that, after it's gone through these rectifiers, it's straight up DC. We don't have AC anymore, okay? AC stops right here, and we have pretty clean DC. You'll notice a capacitor and an inductor right there. That is to help clean up the power, okay? That's one of the functions of the DC link. It buffers and cleans up the power signal, okay, so that we have as true a DC as we possibly can get, all right? So now AC is gone through these diodes, and we've rectified our AC, and now we've got DC. AC's done, okay? So we got our DC, and then as it passes, as it's converted to the DC, all right, now it goes into our inverter section, all right? Now, what these are IGBTs, okay? Let me click there just a little bit more. I want to back up here just a second too. There's one thing I did want you to know, that while you've got 480 volts of power coming in, on the DC bus, okay, it's always going to be higher than the input AC, because we're going to wind up multiplying by root mean square of your voltage. So 480 volts times 1.414, which is the root mean square of 480 there, is what we're going to apply. We're going to multiply it by, and that's going to give us a voltage of close to 600 volts. Okay, so yeah, and like we said, we use this DC for braking. Think about that for just a second. Hold on to that for a second, because we're going to be applying some braking voltage to our motor as well. So this is the section that it comes from. All right. So here we have our inverter. All right, our inverter section. We're sending DC over here, not 3-phase DC, just positive and a negative. Okay. And so we've got what's called IGBTs. These are insulated gate bipolar transistors. Big mouthful there. But these are basically switching mechanisms that allow voltage, a positive or a negative voltage to go to the windings of the motor. And they're switching on very, very rapidly, depending on the frequency. If we have a frequency of 30 hertz dialed in here, it will send a signal out to the motor at 30 hertz, at both a positive and a negative. And each phase for the motor has a set of these IGBTs. All right, so this set's going to send a positive and negative signal to the motor, and then at 120 degrees later, this was going to send a positive and a negative to the motor, and then the third one. So what we've got is 3 different DC voltages going out to the motor. And you're like, wait a minute, hang on, that's an AC motor, but we're going to shoot it with DC? Yes, that's exactly right. Okay, here's how it's going to work. Okay, again, you have a positive and a negative for each phase of the motor. Okay, all right, and this is what we have. This is just one phase. Okay, this is one set of IGBTs. This is a result of them firing. You have the gates that are turned on. Okay, and they're turned on by this processor right here. This processor turns these IGBTs on very rapidly, okay? And so we wind up with the IGBT firing the positive signal with a square wave like this, okay? This is a signal right here going out to the motor. It's a voltage signal, okay? And it shuts off, and then again it fires again, and again, shuts off, again, shuts off, fires again, all on the positive side. Then we turn around and we have the negative IGBT firing, and it does the exact same thing, except for it gives us a negative signal, okay? And it gives us pulses, all right? And then if we have all three of these together, or just, excuse me, before we move into that, what we have here is we have this series of pulses being fired by the processor. It's saying, hey, you said you want me to fire to run the motor at 30 hertz. I'm going to fire these IGBTs at 30 hertz, okay, 30 times a second. All right, so we're firing these pulses, and as we go along, as it's firing these pulses, you'll notice they get a little bit wider each time. Okay. Now this, the vertical axis here that we have, this is our voltage. Okay, and the width that we have these pulses, that is the duration of time that they are turned on. And you'll notice that it's turned on for a very short period of time, and as we progress, we're getting wider and wider. In other words, these gates are staying on longer and longer, and then they start tapering off. They start shutting them off and turn them on less and less, okay? Then the negative IGBT takes over, and it starts doing its thing, and what we wind up with is a simulated AC sine wave, okay? Looks familiar, doesn't it? Okay, well, this is what it's really looking like here, okay? We're turning our pulses on, and I know this slide's probably a little hard to see, but with each pulse, it stays on a little bit longer till it reaches this peak right here, and then it starts shutting them off a little bit sooner. So then, we're starting to get this nice little sine wave, simulated sine wave. This is still DC voltage, but it's simulating an AC sine wave, okay? And then that's just one phase, okay? Again, this is our voltage, okay? Our voltage is staying fairly constant, all right? And this is the amount of time, all right? And then this is the signal here is our current. This is the current that the motor's seeing on each phase. Remember, I've got 6 diodes working for me, one for each phase. So now I've got 3 phases of simulated DC voltage set up 120 degrees apart going to the motor. All right. One of the things you're going to hear when you come to the lab too is when we turn this drive on, the first thing you're going to hear is the way the motor runs. You're going to hear an audible, just a tremendous difference in the way it runs. It's got a pinging, a ringing sound to it, okay? That's because we are pinging it with DC voltage pulses. That's exactly what's going on. And that's why you don't hear it with the AC, because that AC is building and collapsing with the magnetic field and everything. We are firing DC pulses, turning them on and off, and we turn them on a little bit longer, then we start shutting them off a little bit sooner. And that's what's going on with all 3 phases. And these 3 phases are 120 degrees out. So these sine waves are the 3-phase sine waves that we would normally see on an AC motor. The difference is they're DC, okay? So again, our 3 sections is going to be our converter, our input section, the diodes, okay? And that rectifies the 3-phase AC, okay? And it turns it into DC. Once it's left the AC, AC's done. Okay, we don't see AC going to the motor anymore. We have this DC link, and we clean this up a little bit with an inductor and capacitor combination, sort of like a filter. All right, and then we have our power section or our inverter section. The processor here, okay, based on what we tell it the frequency we want it to run, we'll dial in 45 hertz, 50 hertz, whatever it is we want to. The processor says, okay, I'm going to send these signals as positive and negative for each phase based on the frequency you want me to send it at, okay? And we wind up with a simulated AC, but it's actually DC going to it, all right? Now, here's the cool thing about this, and this is between the converter and the DC bus, all right? Say you don't have a 3-phase power source. A lot of people don't. You know, a lot of plants, not plants, but a lot of applications you're going to run across, they won't have 3 phases. You'll only have 2 phases. You only got 2 phases? Well, it's not going to be a problem for us. Why? Okay. Because we're going to take we're going to take 2 phases and we're going to turn it into DC. Okay? We don't need the 3rd phase. In fact, you can run this on single phase, because what we're doing is we are rectifying this to DC. Once it's DC, these take care of making 3-phase for us, simulated 3-phase, okay? Doesn't matter. We can have single phase going into here, and once we get our DC, and we're coming to our IGBTs with DC, controller's going to take over, and it's going to deliver a 3-phase simulated signal to the motor. So that's how we're able to run on 2 phases or even one single phase, okay? The ones here in the lab, for example, where you'll find you're running L1 and L2 to the drive. That's all it needs, and it's going to deliver a 3-phase signal out to the motor. Now, nothing's free though, okay? If you have to do this, then the rule of thumb is you need twice as big a drive. You need to offset your drive for this as well. So instead of having if you're running a 3-phase 10 horsepower motor with a 10 horsepower drive, if you're going to run it on single phase, then you really need to almost double your size of your drive to a 20 horsepower drive to run a 10 horsepower motor. Okay, heat's involved. A lot of heat's involved with this, power factors and things. I'm not going to get into that today, but just know that you don't just get anything for free. You get nothing for free. So if you're going to have single phase available, you're going to have to rate your drive up quite a bit higher. Okay, so that's how we're able to do that. Okay, we have this is where we're going to get into some math here. Okay, so I'm really going to encourage you, if you have to, stop the video and be sure to take notes. But we're going to get into some algebra here. One of the most popular drives is a Hertz Drive. Okay, there are vectorless drives, a bunch of different types of VFDs, but by far the Hertz drive is the most popular. Okay, this maintains the relationship between the voltage and the frequency. In other words, these two stay keep a constant ratio with each other. All right. So like I said, it maintains the relationship between the voltage and the frequency of the pulses being sent to the motor. All right, and motor torque and performance are sacrificed if we don't maintain that ratio. Okay, I'm going to show you how that works mathematically too. So again, to figure a ratio out, it's really quite simple. Volts hertz. All right, we take the voltage and we divide it by the hertz. That's simple. Okay, so our ratio on a 480 volt motor at 60 hertz, running at 60 hertz, is an 8-to-1 ratio. So we want to always maintain an 8-to-1 ratio regardless of the frequency that we run the motor. Okay, if we change the frequency, we're going to have to change the voltage to maintain that that ratio, and the drive does that for us. Okay, so why is this important? Well, you can increase the frequency beyond 60 hertz. The processor that fired the pulses to the IGBTs, okay, it can fire one up to 240 hertz. I've done it before. A motor will fly. It will scream. It's kind of cool to watch. But you can do that by just telling the processor, and you can program one of the parameters, say, hey, maximum frequency is 240. So I can run from 0, surpass 60 hertz, and go well into 200, 240 hertz, okay? But I can't increase the voltage. All right, remember we got to maintain that hertz voltage ratio. Well, I can jump the frequency up, but I can't make more than 480 volts if that's my 480 volt system. I can't make more than 480. So as my frequency goes up and I'm maxed out on my voltage, my ratio is now getting out of whack. Okay, it's not being maintained. All right. So again, the frequency is adjusted by the drive. And the voltage is adjusted by the drive too, but to maintain that ratio up to the point of the input voltage. So it can't go more than 480 volts, okay? So we got to maintain that ratio, all right? So example, if I went if I went up to 70 hertz instead of 60 hertz with my drive, I've had the drive run at 70 hertz, my ratio has now changed because I've divided 480 by 70, I've got a 6.8-to-1 ratio, okay? Here's where this is critical. Motor torque and performance are what is sacrificed when this ratio is not maintained, okay? You're going to get poorer performance. You will not have the torque that the motor is designed to produce when we start operating outside that ratio, all right? mathematically, here we go, okay? First of all, horsepower is speed times the torque divided by 52. This is a constant for us, okay? So just kind of ignore that right now for right now. So the horsepower, the rated horsepower is developed by the speed times the torque divided by 52. All right? Doing a little bit of algebra here, okay? Let's suppose we have a 100 horsepower motor. I'm going to make this one up, okay? I got a 100 horsepower motor. My speed is 1800 RPM, okay, times the torque, which we don't know right now. That's what we're trying to figure out, the torque, okay? So in order, and we divide that by 52. In order to, what we're trying to do is get T by itself through algebra. We have to multiply this over here, this by 52 over 1, okay? Well, we do that, but we can't do one side, we can't multiply it by one side without multiplying it on the other side. So what we have now is we've gotten rid of the 52, and we're left with 1800 times the torque, and we've had to multiply the 100 by the 52. This is what we wind up with at this point. 525,200 equals 1800 times the torque. Okay, that's our algebraic formula at this point. All right, so moving forward, what we're going to want to do is try to get, again, torque by itself, because that's what we're looking for. All right, so in order to do that, we'll divide each side by 1800. That eliminates that and gives us just a T. And then we'll divide the 525,200 by 1800, okay? And that gives us a torque of 290 foot-pounds for our torque, okay? We finally got T by itself. So now we know what our torque is for our formula. Let's go back and plug it in, okay? So we have, we can check it as well too. So 100 horsepower is going to equal 1800 RPM for the speed, 291 foot-pounds for a torque divided by 52, and that gives us our 100 horsepower, okay? Now, that was a lot to, I'm glad you could pause this video because you might want to back it up a little bit and review that, okay? But algebraically, that's how we found the torque, all right? So now let's change the, instead of the 1800 RPM at 60 hertz, let's change this to where we're going to run that motor at 3600 RPMs. I want you to see what's going to happen to the torque, okay? Because now our hertz is going to go beyond 60. We're going to lose that ratio. We're not going to maintain that ratio anymore. So now let's look and let's ramp that speed up to 3600. Let's plug it back into our formula, okay? Because again, we're going to look for torque, and we're going to see the impact that doubling the speed of an RPM of a motor is going to give us, what's going to make on the torque, okay? So using our formula again, horsepower equals speed times torque divided by 52. We have a 100 horsepower motor, we know that. We're going to run it at 3600 RPMs. We're looking for T, and we're going to this should be divided by 52, okay? All right, so we divide the 52 on each side, or multiply it on each side here, okay? All right, and we get rid of the 52. We got to do it to the other side. And we got 100 times 52. This is equal to the speed times the torque, okay? And again, we're trying to dial down to get this by itself. In order to do that, we're going to have to divide both sides by 3600. So let's do that, okay? By 3600. All right, and now we should have T left, okay? So our T should be divided by 3600, gives us our T by itself. And now we've got 145 foot-pounds. If you want, I'll go over this with you in person, okay? I'm sure it's kind of probably hard to follow in this video. But what we've done is we have doubled the RPM of our motor, and as a result, we've lost half of our torque of our motor. So our motor's not going to be able to put out the full horsepower that it's supposed to be rated at, because we've doubled the speed of the rotor, and in doing so, we have sacrificed the torque. That's why we've got to maintain that ratio. Anything below 60 hertz, we can maintain it because the voltage and the hertz can stay together with the ratio. Okay, we've maxed out on 60 hertz and the voltage is maxed out. Okay, now my processor can make it go higher, but I can't get more than 480 volts out of that, okay? So that's where our ratio starts to drop off, and as a result, our torque drops off because our frequency is going up. We're spinning it faster, but we're losing torque, okay? That's a lot to take in. Right now, I just want you to go ahead and stop the video. If you want to back up and try to review that algebraic formula to figure out how that ratio is important, that's a good idea to do that. Also, if you have a problem, if you have a problem understanding that, come see me. We'll work it out on the board, okay? For those of you that have not had algebra in a long time, it's probably a good idea. We can come and refresh and everything. But for right now, I want to stop the video, kind of take in what you've gotten so far, and we're going to move forward from this point on. So I'll do this on the second part, but for right now, just stop the video, kind of rest, absorb what we've talked about, and we'll come back and watch the second section of this, okay? So otherwise, we'll see you in just a little bit.